Here's a couple of ways to determine the limiting reactant, all right, of a reaction. Let's say that I have H2 reacting with N2, hydrogen gas and nitrogen gas react to form NH3, ammonia. Now, first off, when you're dealing with a limiting reactant problem, make sure that the equation is balanced. All right, you're going to need the mole ratios. We're going to talk about that later, but it's very important to have your equation balanced. And I'm going to put it 2 here because the nitrogens are now the same. Notice how now I have 6 hydrogens on this side, but I only have 2 hydrogens on this side. But if I multiply this hydrogen by the 3 times 2 gives me 6, and now the hydrogens are balanced. So this is looking like a balanced equation. Now, let's say if instead of this is like sort of the ideal reaction, all right? So ideally what would happen is that you have 3 moles, right? You have 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas to produce 2 moles of ammonia. And that's the ideal scenario. But a lot of times when you're doing chemical reactions, it's not going to be perfect, right? There's going to be maybe some amount that's left behind, some excess amount, right? Maybe the thing's not going to react, fully, completely as you expect it to. So a lot of times, right, you're not going to be given, these crazy good ratios. And instead, maybe you're given that you have 4 moles. Let's just say you're given that you have 4 moles of H2, and then you have, let's say, 1 mole of N2. All right. And you're trying to react these together, and you want to see how much NH3 will you produce. All right. How many moles of NH3 will you produce? So just looking at the information that I have, I can already tell that, well, I'm going to have some extra H2 left behind. And how do I know this? Well, the original reaction was 3 moles of H2 reacting with 1 mole of N2. But in this reaction here, I have 4 moles of H2, but I still have the same amount of N2. So you can see now I have some extra sort of hydrogen gas left behind. So this right over here, this hydrogen gas is what I would call an excess. All right, this hydrogen gas would be an excess because, well, you have excess amount of it, right? It's a little too much for what you're dealing with. And that means that my N2 is going to be something known as a limiting reactant. All right, sometimes it's called a limiting reagent, but this is going to be called a limiting reactant. And the reason why it's called a limiting reactant is the amount of N2 in this case actually limits how much product can be made, right? Because we have excess amount of H2, then that means that the amount of N2 has to limit the amount of NH3 that we produce. Now, how do I actually find out the amount of NH3 I produce? Well, one way to do this is essentially you can use mole ratios to compare how much NH3 you would make using this original equation right over here, and then you just choose the one that produces the least amount of moles of NH3. So let me give you an example here. So we know that I have 4 moles of H2. All right, I'm gonna do this part for H2 first. All right, now 4 moles of H2, and what I'm gonna do now is I'm gonna look back at my original reaction written up here. And I'm gonna say what is sort of the perfect amount of NH3 that I can make. In an ideal scenario, if I have 3 moles of H2, right? If I have 3 moles of H2, then I can make 2 moles. I can make 2 moles of NH3. That is the ideal scenario. So if I multiply this by the ideal scenario, and I put this into a calculator or whatever, I'm going to get 2.66 blah 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 blah. It's going to be repeating on forever moles of NH3. Don't worry, I'm not really going to worry about sig digs for now. We're going to get into like significant figure stuff when we actually do a practice problem. So, but for now, this is just demonstration purposes, all right? But don't forget sig figs when you're actually sig digs, whatever, when you're doing an actual problem. Now for N2, I know that I have 1 mole of N2, right? 1 mole of this. And in an ideal scenario, once again, we look back at our original reaction and we say, ideally, 1 mole of N2 creates 2 moles of NH3. So then, when I do all of this, I'm just going to get 2 moles of NH3 in my scenario. All right. And so because the amount of N2 that I have produces the least amount of products, right? This produces the least amount of NH3 here. Well, this is going to be my limiting reactant. This is going to limit how far my reaction goes. If I stuck with the hydrogen gas, right? If you go with the hydrogen gas, you're going to produce this many moles of products, right? It's capable of producing 2.66 of blah, 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 blah moles of NH3. However, our reaction is only limited to 2 moles of NH3 because that's how far this reactant goes. If this reaction, reactant can only go to 2 moles of NH3, well, then the other can't kind of sort of go to its true capacity, right? The other can't go this far because, well, you don't have enough N2, right? So that's how you kind of do these problems. You check how many products each of them would produce under sort of the ideal mole ratios, and you just choose the reactant that produces the least amount of products. Another way to sort of find out the limiting reactant is you just compare the mole ratios, right? So normally the ratio of hydrogen to nitrogen gas in our original formula, you can see that's a 3-to-1 ratio, right? So I'm just going to write 3/1 here. However, given, I have 500 moles of N2 and 2 moles of H2. And obviously, I mean, just from looking at this, you can just see that, well, we have so much nitrogen gas, but we don't really have enough hydrogen gas. So hydrogen gas must be my limiting reactant. But another way to kind of do this, if you're, unsure about this, is you just write out the same ratio. Normally, ratio of hydrogen to nitrogen is 3-to-1. In this case, it is 2 to 500. And that's the same thing as just 1/250. But you can see that 3 is clearly greater than 1/250, of course, right? So you can see how my numerator in this case is very big, but in the second example here, my numerator is very small, and it's actually my denominator that's very big. So what's on my denominator? Remember, it's hydrogen gas divided by nitrogen gas, right? So it's hydrogen gas divided by nitrogen gas. And you can clearly see that we have way more on the denominator than on the numerator. So therefore, I know that I have an excess amount of nitrogen gas because my denominator is bigger than my numerator now, right? And then, that means that H2 has to be my limiting reactant. Okay, we have 2 moles of aluminum reacting with 3 moles of chlorine gas to produce 2 moles of aluminum chloride. We start off with 10 grams of aluminum, 50 grams of chlorine gas. We want to find the limiting reactant, first of all, the amount of AlCO3, this should say 3 here. So we want to find out the amount of products that I actually produced, which is, we're going to talk about theoretical yield and percent yield and all of that. And finally, we're going to find out the mass of the excess. All right, so if we have excess, well, how much is it? How much of it is actually in excess, right? Now let's get started. First of all, we're given grams. And in these types of problems, I want to work with moles because that's how I activate my mole ratios. So if I look in my periodic table, let's just take a deep look in my periodic table, and we see that aluminum has a molar mass of 26.98. I'm just going to round to 4 digits. So if I have 10 grams, 10.0 grams of aluminum, right, that's going to be 26.98 grams for every 1 mole. All right, that's the molar mass for aluminum. And for my chlorine, well, a singular chlorine atom has a molar mass of 35.45. So for my chlorine, I have 50.0 grams of chlorine gas, and 1 mole of chlorine gas weighs. This is where things get really tricky, because what you're going to do is you're going to take this 35.45 and you're going to multiply it by 2. All right, so this is the amount of grams for 2 chlorine atoms, because remember, in my periodic table, 35.45 represents the molar mass for 1 chlorine atom. But because chlorine is a diatomic, there's 2 of them, meaning that I just have to take this value for 1 chlorine and multiply it by 2. So I get the correct molar mass for chlorine gas. All right, so here's what I got. And don't forget that this is the amount of, on the top here, this is the amount of moles of aluminum. And then in the bottom here, this is the amount of moles of chlorine gas that I have. And I know I put this ... here because this is like a very, very long decimal. And the thing is that I want to do my rounding at the end of the problem. So, it's not really wise to round at the middle of our problem. So I just left it like this. And yeah, we started out with 3 significant figures. So we have to end off with 3 significant figures. So just be aware of that as well. All right, so now we have that many moles of aluminum. All right, and once again, we're going to do the same trick as we did earlier. We are going to say that ideally, under ideal conditions, if I have 2 moles of aluminum, I'm going to get 2 moles. I'm going to get 2 moles of aluminum chloride. That's the ideal scenario for this amount of aluminum that I have, right? And for this amount of chlorine gas that I have, the ideal scenario would be that, well, if I have 3 moles of chlorine gas, then, well, that's going to give me 2 moles. That's going to give me 2 moles of aluminum chloride, right? That's the ideal scenario for this So we're just going to, you could also just do all of this in one step. That would probably just be more efficient, but it's all right. I just plugged all of this into my calculator and compare the two values, right? With aluminum, I'm able to make this much aluminum chloride. With this much chlorine gas, I'm able to make this much aluminum chloride. So take a look, which value is smaller? Aluminum's value is smaller, and that means that aluminum must be the limiting reactant. Now, this is a very important idea to get, which is that the reaction is driven purely by the limiting reactant, all right? The amount of products that is produced is purely driven by the limiting reactant. So because aluminum is our limiting reactant, well, then this is actually the amount of products that's going to be created, all right? And there's going to be, of course, some of the chlorine in excess. So yeah, let's work from here. We're trying to find out the mass of our products that's going to be produced. So because our reaction is driven from the limiting reactant, which is aluminum in this case, well, then I'm going to take the amount of moles of aluminum chloride from the aluminum side, right, from the limiting reactant side, and I'm going to say, okay, for every 1 mole of aluminum chloride, and then we want to find out the amount of grams in 1 mole. So we have to find the molar mass of aluminum chloride. So aluminum, that's 26.98. 6.98, and we have 3 chlorines, so it's going to be plus 3 multiplied by chlorine's molar mass, which is 35.45. Okay, I added all of this up and I got approximately 133.3 grams. So then when I multiply these out together, I put this into my calculator and I got 49.4 grams of aluminum chloride, and that's going to be the theoretical amount of, or the theoretical yield, of the mass of AlCO3 produced. Now we want to find the mass of the excess region, all right? Now to do this, recall all the way back to when you found out the amount of moles of CO2, all right? This is the amount of CO2 that is available for your reaction to use. Now it looks like you have produced 0.3706 moles of aluminum chloride. So let me just take this value right over here. Let me just take this value. And we can use this, once again, using mole ratios to calculate the amount of chlorine that is used in the reaction. So we have this many moles of aluminum chloride. And we know that for my reaction, 2 moles of aluminum chloride, and then 3 moles of chlorine. So 3 moles of chlorine react, or 3 moles of chlorine gas react to form 2 moles of aluminum chloride. So that's my mole ratio. And if I do this calculation, once again, you can cancel out the units as you like, but we're going to get 0.5559 moles of chlorine gas that's actually being used up in this reaction, right? Just from this mole ratio, from our limiting reactant, we can actually find out the amount of chlorine gas that is actually used in the reaction. Now, if we compare this to the amount of moles of chlorine gas that we actually have, notice how there's an excess amount. And if I take these two values and I subtract it, well, I'm going to get my excess, right? The amount of chlorine gas I have available minus the amount of chlorine gas I have used is equal to the excess amount, right? Essentially the amount that didn't react. So I just did the calculation here. And if I have this many moles of CO2 in total minus the amount that's actually used, this is the amount of CO2 that I have in excess. Now remember what the problem is asking. We're trying to find the mass of our excess. So we have to take the moles of the excess amount that we have and essentially convert it to grams, right? Because we're trying to find the mass. So if I actually do that, I get 10.6 grams of CO2. Remember to round to the correct number of sig digs. Remember, we started out with 3 sig digs, so we got to end with 3 sig digs, and that's going to be my answer. Now let's just talk about the idea of a percent yield, which is actually just much simpler than it sounds. Literally, look, from the last practice problem that we did, we found out that 49.4 grams of aluminum chloride will be produced from our limiting reactant problem. All right, that's our sort of expected amount. However, if you're actually doing this amount in a lab, well, then the actual amount of aluminum chloride that you have might be a little bit off, and that's, perfectly fine. There might be some error. Maybe some of it dropped off the table or something, right? So you get less than maybe what you expected. So your theoretical yield would be essentially the result that we got from completing the problem, right? This is essentially the amount of aluminum chloride that we expect to get. However, the actual amount is, well, the actual amount you get from doing the lab. And this essentially gives you the error, right? How far off were you from what you expected to get? So in this case, the actual amount of aluminum chloride that I got from my lab was 45.9, 45.2 grams. However, I was expected to get 49.4 grams. So remember, we have to multiply all of this by 100 actually, right? Because we want to turn this into a percent. So we have to multiply this by 100. And if we do this, we get, I plugged this into my calculator and I got 91.5% yield. All that means is that, well, I got 91.5% of what I essentially expected to get. Now, we're going to get into the idea of combustion analysis, but first, you gotta know how to do empirical and molecular formula problems. So let's just do this one first. So we say a compound is found by mass percent to contain 40% carbon, this percent hydrogen, this percent oxygen, and if the molar mass is 180.2 grams per mole, we want to find the empirical and molecular formula. Just a little refresher, if we have something like, let's say, C6H12O6, right? C6H12O6, of course, this is glucose, and this is the molecular formula for glucose, right? However, I can simplify this, right? Imagine if this is cursed, but imagine if I divide this by 6. Then carbon divided by 6 is going to be, well, just 1 carbon, right? I have 12 hydrogens. 12 divided by 6 is 2. And 6 divided by 6 is just 1. So sort of the simplified version of what I originally had of the molecular formula is the empirical formula. Empirical formula is literally just the molecular formula, except you express it in sort of the simplified form, right? So let's actually do this problem. So first of all, when we're doing these types of problems and you're given these percentages, we're just going to assume that we have 100 grams of this. So assume that we have 100 grams of, well, our compound. Because if we have 100 grams of our compound, we know that 40% of it has to be carbon. So that means that 40.00 grams of it is carbon. That means that 6.71 grams of it is hydrogen, and 53.29 grams of it is oxygen, right? So if we're assuming 100 grams, we're essentially converting the percentages into actual grams that we can use for calculation purposes. Now let's just convert all of them into moles. So if I have 40 grams of carbon, one mole of carbon is approximately 12.01 grams of carbon. So using that molar mass, I get 3.33. So I'm just going to say 3.5. So I'm just going to move all of this. Sorry, guys. So I get 3.5 here. And if I do the same thing for hydrogen, well, hydrogen, it has 1.008 grams of hydrogen for every 1 mole of hydrogen. That's the molar mass of it. So once again, I literally just do this for every single element that I have. I know this is a little bit repetitive. Now this is 6.66, or I'm going to just write 6 2/3. And then finally, I can convert the amount of oxygen I have into moles. I know that in 1 mole of oxygen, that's 16 grams, approximately. So 53.29 divided by 16, that's also going to be 3 1/3 about. Now what you're going to do is you're going to try to divide every one of these numbers by the lowest number. So you see here, 3 1/2 is the lowest number. So I'm just going to divide everything. Imagine if I divided everything. I'm going to divide everything here by 3 1/3. And if I do this, 3 1/3 divided by 3 1/3 is just going to be 1. So that means that I'm going to have 1 carbon. 6 2/3 divided by 3 1/3, that's going to be 2. So that means you're going to have 2 hydrogens. And finally, 3 1/3 divided by 3 1/3, once again, that's just going to be 1. If you ever get like a weird number, like let's say 1.5, right? Let's say if I somehow did the division and I got 1.5, then what you would do is notice how, actually, let me just do it here. Let's just say somehow I got 1.5 oxygen, all right, for some practice problem. Then what you would do in this scenario is you would just multiply this entire compound by 2. You just multiply the amounts by 2, all right? Because notice how if I multiply this entire compound by 2, I get C2H4O3. Remember, these chemical formulas, you always need whole numbers, all right? So in this case, we only have 1 oxygen. I just put that there for example. So there's our formula. That's our empirical formula, all right? Everything's simplified. Now, what is the molar mass of this? We said, you see that the problem gives us the molar mass, and we're actually able to calculate the molecular formula. It's very important that the empirical formula is just a multiple of the molecular formula, all right? So what that means is if I take the molar mass of, well, C1H2O1, so that's going to be 12.01 plus 2 multiplied by 1.008 plus 16, I get 30.03, all right, grams per mole. That's my molar mass for this. And notice how this is essentially a multiple of, or notice how 180.2 is essentially a multiple of 30.03, right? If I multiply this value by 6, imagine if I multiply, sorry guys, if I multiply this value by 6, then I get my molar mass. And that makes sense, right? Because remember, the empirical formula is the simplified version of the molecular formula. So you're essentially dividing the molar mass of your molecular formula by some constant to get the molar mass for your empirical formula. And for this problem, we're just basically reversing that step. All right, we're given the molar mass, and we can also calculate the molar mass for my empirical formula. So if I divide 180.2 by 30, I get a multiple of 6. And all that means is that, well, I essentially have 6 times of everything inside my compound. So what I'm just going to do is I'm just going to multiply everything here by 6. All right, that's what this multiple means. I have 6 times as many carbons, hydrogens, and oxygens in the molecular formula than my empirical formula. So if I do this, I get C6H12O6, and we have our answer. Here's our combustion analysis question. So we have 0.500 grams of an organic compound, and that organic compound contains carbon, hydrogen, and oxygen. Now this is burned, and the combustion is going to yield this much CO2 and this much H2O. And we want to determine the empirical formula for our organic compound. Now, the thing is that, well, combustion reactions, you're going to have carbon, and we don't know how much carbon we have, so let's just put X here. We're going to have some amount of hydrogen. In this case, we don't know how much hydrogen I have, so I'm going to put a Y here. And we also have oxygen in this compound, right? And I don't know how much oxygen I have. I'm just going to put a Z there. In a combustion reaction, you have your hydrocarbon, which can contain carbon, hydrogen, and then maybe in these problems you might see another element. So in this case, I see oxygen, and I'm going to react this with oxygen, and that's going to produce water and CO2. Okay. Now we said that the combustion yields 1.1 or 1.1 this many grams of CO2, and we formed this many grams of H2O, and we started out with 0.500 grams of our organic compound. So how do we determine how much carbon, hydrogen, and oxygen we have in our compound? Well, the thing is that, notice how in CO2, right? Notice how in this entire reaction, you have a carbon here, and you have a carbon here in my CO2. And what this implies is that all of the carbon that I originally had to start, right? All of the carbon that I sort of started out with, well, that's all of the carbon that's going to be found here, right? All of the carbon here is going to be found here because this is the only term with a carbon that's on the product side, right? And then likewise, all of my hydrogen that's going to react is going to be found in all of the hydrogen in my H2O, right? Because, well, you see how H2O, this is the only product that contains hydrogen, right? So I know that these two hydrogens, they must, be the same amount, right, that reacted. So I'm essentially going to work backwards from the products and find out the amounts of carbon and hydrogen. Let's start out by calculating how much hydrogen I have in my original compound. So in this case, this is the amount of products that I created, right? And let's convert this into moles. So I have this many grams of H2O, and when I convert this into moles using my molar mass, well, I'm going to get some result. And what I'm going to do next is I'm going to say, okay, I see H2O here. And if I'm trying to find out the amount of hydrogen that I have, well, I know that in 1 mole of water, in 1 mole of H2O, I have 2 moles of water. I mean, not 2 moles of water, but I have 2 moles of hydrogen, right? In 1 mole of H2O, I have 2 moles of hydrogen. So notice how grams of H2O essentially cancels out here, or grams cancel out here. The moles of H2O cancels out here. And the unit that you're left with is the moles of hydrogen. And that's exactly, what we want if we want to do any calculations. Now I'm going to take it a little bit further here. And for these types of problems, you're actually going to do an additional step. You're actually going to convert the amount of hydrogen that you have into grams of hydrogen. So in this case, 1 mole of hydrogen, I know this is a lot, but 1 mole of hydrogen is about 1.008 grams. All right. So I essentially converted from grams of H2O to grams of hydrogen. All right. And when I put all of these into my calculator, let me see what I get. All right. So using the calculator, I found out that out of the 0.500 grams that I originally started with, right, out of the entire sample that I originally had, well, 0.04999, or sorry, 0.0499 grams of that is going to be my hydrogen. Now let's calculate the amount of carbon that I have in grams. So once again, because I'm trying to solve for the amount of carbon that I have, I'm going to use the CO2 term. I'm going to say, okay, I have this much carbon. I have this much carbon dioxide. And I'm going to say, well, what's the molar mass for carbon? These are simple sort of molar masses that you probably should memorize. A single oxygen atom has a molar mass of 16. So if I have two of them, that's 32. And a single carbon atom has a molar mass of 12.01. So if I put those together, I get 44.01. So 44.01 grams for every 1 mole of CO2. And I know that in 1 mole of CO2, I'm going to get 1 mole of carbon. See, now we're doing the same thing that we did before, right? We're converting from grams of carbon dioxide to how many moles of carbon dioxide do I have, into how many moles of carbon do I have, into how many grams of carbon do I have, and that's going to give me the grams for the carbon in my original compound, which is very, very nice. So I'm going to do all of this. This many grams, and it's just plug and chug into the calculator. Okay, so I found out the amount of carbon that I have, and I found out that this is 0.3007 grams of carbon. Now, how do I find out the amount of oxygen that I have? Oh, this is a very clever strategy. I know that my compound is made up of carbon, hydrogen, and oxygen. And I know that the total mass for my compound is 0.500 grams. So if I have the mass of the carbon in my compound and I have the mass of the hydrogen in my compound, what I can do is I can just take my total mass. I can take my total mass and I can subtract it from the amount of carbon that I have, and subtract it from the amount of hydrogen that I have, right? Okay, so when I subtracted the total amount of my sample by the amount of carbon and the amount of hydrogen that I have, it turns out that I have 0.1494 grams of oxygen. All right, now, just like how we did with the empirical problem formula thingy, well, we're just going to convert all of these to moles, divide by the lowest number, and then we should get a nice answer. Okay, I converted all of these to moles. I got these answers right over here. Notice how my lowest value is this 0.00933. So let me just divide everything by 0.00933, and let's see what I get. And whoa, when I divided everything by this, my formula turns out to be C 2 2/3, H 5.35, and O1. This is not whole numbers, of course. So what I'm going to do here, I'm just going to multiply everything by 3. 2 2/3 multiplied by 3 is just going to give me 8, right? So just 5 and this is around 5 1/3, right? This is approximately 5 1/3. So 5 1/3 multiplied by 3, well, what is that equal to? I'm just going to do it on my calculator because I don't trust myself, but yeah, this is going to be 16 hydrogens, so H16, and of course 1 times 3 is going to give me O3. And that is the answer to this problem. All right, this is going to be the empirical formula of my mystery compound. And it turns out that, well, if we found out the molar mass of this, and then maybe this problem was asking us for, let's say, the molecular formula. And let's say that the molecular formula's molar mass is the same as our empirical formula's molar mass. Well, then our empirical formula is just going to be the same thing as our molecular formula. For example, take carbon dioxide. Let's just call this our molecular formula, right? This is our molecular formula. This is our molecule, right? But it turns out that, well, we also cannot simplify CO2 into any simplified form, right? It's already in its simplest form. So it turns out that the molecular formula for CO2 is the same as the empirical formula for CO2, and that's completely fine.